Okay, welcome to Hariri Institute Distinguished Speaker Seminar. My name is Yannis Paskalidis, and I'm the director of the Institute. Just a quick check, Tessari, can you see the slides? Okay.
I can see the slides.
Okay, perfect. Okay, so I'll take just a few minutes to introduce the distinguished speaker series of the Institute, and in just one slide telling you what the Institute is about is BU's Federation for Computing and Computational Science and Engineering, and it has a number of different centers and initiatives that live under the Institute and provides common infrastructure for all of these centers and initiatives. And as you can see, they span pretty much everything under computing and computational science and engineering, fairly broadly defined. The Distinguished Speaker Series is a seminar series where we invite very distinguished people. So today we have the pleasure of Arvind Narayanan that will be introduced in a moment to give the seminar. I just want to mention a few of the events that are coming up for the rest of the semester. In late November, we have Milin Tambe from Harvard that will give a distinguished seminar. At the end of November, we have an AI and education symposium that is focusing on the AI and specifically generative AI impact in education, an extremely important and hot topic these days. And mid-December, we have Sharon Huang, who is at Penn State, that will give an invited distinguished seminar as part of the AI research initiative, which is part of the Institute. This is where you can find us on LinkedIn, Twitter, Instagram. And I should mention that today's talk is going to be recorded, and we will make the talk available to you after the seminar through our YouTube channel. So in terms of logistics, please hold any questions. You may, during the talk, pose any questions through the Q&A feature, and Tessari Lin, who is the host for today's seminar, will summarize the questions at the end and will pose them to Arvind. So I will next, what I would like to do is I would like to introduce today's host. Tessari Lin is an Isabel Anderson Career Development Assistant Professor of Marketing at the Questrom School of Business at Boston University. She's also a junior faculty fellow at the Hariri Institute and faculty affiliate of the Technology and Policy Research Initiative. Tessari's research focuses on how information and data moderate the relationship between firms and consumers. She is working on a number of different topics, including privacy preferences and their impacts on firm analytics, analytical tools that adapt to the privacy-first data landscape, and understanding how companies use choice architecture to moderate consumers' data sharing decisions. So Tessari had joined BU relatively recently, received her PhD in quantitative marketing at the University of Chicago, and before coming to BU, worked for Microsoft Research at the Chief Economist Office of Microsoft Research and at JD Silicon Valley Lab. So Tessari, the floor is yours to introduce today's distinguished speaker.
Thank you so much, Yannis. It's my great pleasure to introduce our distinguished speaker today. So Arvind Narayanan is a professor of computer science at Princeton. He is also a director of the Center for Information Technology Policy. And Arvind led the Princeton Web Transparency and Accountability Project to uncover how companies collect and use consumers' personal information. His work was among the first to show how machine learning reflects cultural stereotypes And his early research showed the fundamental limits of the identification techniques. I'm personally a big fan of his work on privacy and also his recent newsletter called AI Snake Oil. So for anyone who is interested in learning more about the capabilities and limitations of AI, I highly recommend you to check it out. Arvind has won numerous awards for his work. So anyone who is interested, please go to Arvind's website and check it out. I also want to say another thing that that's so amazing about Arvind is his ability and willingness to convey his insights about these important topics to the public. So with that, I want to thank you, Arvind, for this important work. For today, Arvind will give a talk titled "The Reproducibility Crisis in Machine Learning-Based Science." Again, so for the audience in the room, if you have any questions, please feel free to type them in using the Q&A feature. I will summarize them towards the end of Arvind's talk. Okay, so with that, please join me to welcome Arvind Narayanan. And Arvind, the floor is yours.
Thank you for that kind introduction. It's great to be here. Let me take a moment here to get my slides up. Let me say a couple of things to give you a sense of what kind of talk this is. It's going to be a relatively high-level talk. I'm going to try to cover a lot of ground. It's based on a couple of papers, and those papers are going to have a lot more detail. And I should also say that this talk is mostly bad news. I think there will be some slivers of good news in between, but most of it is it's going to be bad news. Okay, so on that cheery note, let's get started. Let me start with a story. Epic, which is a healthcare technology company, in 2017 built a machine learning model to detect whether a hospitalized patient was going to develop sepsis. And that's a big deal in hospitals. You want to physicians want to have early notice of developing sepsis so that they can treat it and avoid unnecessary deaths in the hospital. Hundreds of hospitals deployed it. But the first time that the system was rigorously evaluated by someone other than Epic was many years later in 2021. And you can see the reference at the bottom. And what they found was that the accuracy of sepsis prediction, the accuracy of this classifier in terms of AUC, area under the curve, was only 63%, as you can see, or 0.63, as you can see in this chart here. And what Epic had claimed, without really releasing any data, was that the performance was between 0.76 and 0.83. And of course, for AUC, 50% is random. So in a sense, the model is only between half to 1/3 as accurate as Epic had claimed it was. And this was a big deal. And beyond these numbers, in a qualitative sense, physicians found that the model was just overwhelming them with false alerts and still missing the majority of sepsis cases. And when this news came out, Epic actually stopped selling this one-size-fits-all model, but only after a lot of damage had already been done by deploying this to hundreds of hospitals. So what happened here? Why were Epic's claims incorrect? Why was its accuracy much lower than Epic had measured? Epic wasn't trying to mislead people. They had just gotten the measurement wrong here. So what happened was there were many errors with their measurement, but one notable one I found was that in building this model, one of the features that Epic had used was whether antibiotics had been prescribed to the patient for sepsis, right? So in other words, as you can see in the story, what the model is doing is it's predicting sepsis after the physician has already diagnosed sepsis and started treating it. And so, of course, in those cases, it's quite useless. And I don't think you need experts to point this out. I think this is fairly obvious once you understand what's going on. But it's often tricky when you have a machine learning model with perhaps hundreds of features to recognize that one of those features, is going to lead to over-optimistic evaluation. So this is a type of leakage. Let me give you a definition of leakage. Leakage is a spurious relationship between the independent variables and the target variable. So in this case, antibiotics and sepsis. So leakage might arise because your data collection or sampling or pre-processing strategy had something wrong with it. And because the spurious relationship is not going to exist in the real world when you then try to predict sepsis in a hospital, what it means is that the performance you've measured when building and validating the model is going to be over-optimistic compared to what you're actually going to get in the real world. And so this is what we're calling a reproducibility crisis. And I've given you one example, and the crisis, it's a bit of a fighting word there. So let's see if I can justify that in the next half hour or so. So it's more than this one individual example. The reason we're calling it a crisis is that in more than a dozen fields, all of these fields have recently started adopting machine learning methods, and that's great. But I think they've been adopted rather haphazardly, and systematic reviews have found that large fractions of the studies that they sampled were in fact faulty, and in all cases due to leakage. The reviews themselves were in disparate fields, and we noticed that looking across all of these fields, leakage seems to be a common problem. So here's a massive table. I don't mean for you to read all of this here, but just in terms of how to read this table, this is the field, and then the people who did the systematic review. So these were not the flawed papers. These were the authors who analyzed the flawed papers, and the number of papers they sampled and the number where they found pitfalls. So for instance, this row means that in clinical epidemiology, 48 of the 71 papers that were sampled had leakage, and in satellite imaging, 17 out of 17 had leakage, and so on. So I think this is really happening everywhere, especially in medical fields. But I think that's really more of a consequence of who is even bothering to do these systematic studies than anything else, because in medicine, the consequences are so serious. And I suspect that this is in fact happening in a lot of fields not represented on the slide. It's just that no one has bothered to do this kind of systematic review. And so we have a couple of papers on this, as you can see here. The first one is the main one that I'm going to be presenting today. It's specifically about leakage. And the second one is a collaboration of 19 researchers from many different fields, thinking about what kinds of remedies we can have, not just for leakage, but for the broader reproducibility crisis that I will explain. And, frankly, my assumption is that, as you can see on the slide, but also just based on my intuition, based on some other analyses that I've done, is that in many fields, the majority of machine learning based research is wrong or over optimistic. I think the state of affairs right now is not very good. And leakage is a major problem, but it's only one of the problems. Okay, so that was the first point I wanted to communicate, that this is very pervasive. Oh, by the way, I almost forgot. So one of the fields here is computer security. You can see that near the bottom. And a fun fact, in a previous life, I was a computer security researcher. And one of the flawed papers analyzed in this systematic review is one of my papers. The lesson I take away from that is that even for researchers whose shtick is to point out the limitations of machine learning and the difficulties of machine learning evaluation, we tend to, I think, also get over-optimistic when we're using machine learning in our applied ML work. And frankly, after I started doing this leakage work, I realized that if I were to go back to all of my past applied ML work, there are probably more papers that are susceptible to leakage. So this is not a problem of, some of these are issues of real carelessness, but in other cases, even folks who know better than to avoid these problems and who are trying to be careful, I think there are some real subtleties here. So let me explain why some aspects of the leakage problem are really hard. And it's because it lies on a spectrum. It lies on a spectrum between relatively straightforward errors on the one hand and distribution shift on the other hand. So what do I mean by this? Across the spectrum, I will point out a few particular types of leakage or reproducibility issues. The first one is no train test split. I assume no one listening to this is going to build a machine learning model where you don't do a train test split, but it is surprisingly common in published peer-reviewed work. I'll give you an example in a couple of slides. A somewhat more subtle one is machine learning, as you might know, relies on the assumption that the data, the train and test samples come from the same distribution and they're independent, et cetera. And if those assumptions are violated, there's going to be a problem. So sticking with the medical domain, to pick some examples, let's say you're working with a hospital data set. And in that hospital data set, there are different families And it could be that people in the same family have correlated outcomes. And so if you split your samples randomly into train and test, what could happen is that the model, if it's sufficiently powerful, could memorize some of these patterns from one family member and apply it to another family member. So that's a very subtle kind of issue. The way to avoid that is to split by family, to keep families together. In other words, train on some families and test on other families. And we know how to do that, but can you think of all of the possible violations of the independence assumption? And do you even have the data in your data set, the annotations in your data set, to know that certain people belong to the same family? So those are genuinely hard questions. And then you move further to the right of the spectrum. Let's say the issue is that you train on some hospitals, but now you want to deploy the model to other hospitals where the population might be different. Or the disease itself might change over time. You build a model for COVID prediction today, but COVID quickly evolves over time. So next year, things might be different. So that's an issue of concept drift. And more broadly, that's an example of distribution shift, where the train and test distribution are going to be different for reasons that are really outside your control. So what do you do about that? That's, as you might know, its own research area. One thing you can do is build machine learning models to do more causal inference type things. If models are informed by causality, then the hope is that they're picking up on patterns in the data that have a causal validity and therefore are not going to change too dramatically when you move to a different hospital or location or a different distribution. But again, that's not straightforward. And so there's a wide variety of issues here. And the point is that where exactly does leakage end on the spectrum and where does distribution shift start? I don't know. It's kind of a smooth spectrum. Okay, so I think when it comes to leakage, the best thing we can do is to be aware of all of the different types of leakage and just to make sure that none of these occur in our research. And if they do occur for reasons that we can't avoid, we have to be very explicit in how we communicate that research. And so we've done that work so you don't have to. We've looked at hundreds of papers. Basically, we looked at all of the papers covered in the systematic reviews in the slide that I showed previously. So that includes hundreds of papers from over a dozen fields. And it turns out that there are 8 different types of leakage. Across these hundreds of instances, they all cluster into these 8 categories. I won't go into too much detail on what each of these 8 are, but as you can see broadly here, the first major category is a lack of a clean separation between train and test. So simply not splitting at all is an obvious way where things can go wrong, but there are less obvious ways. For instance, you might do the feature selection before you do the train test split. And that tends to happen very commonly, and researchers genuinely don't recognize that when you do that, you're introducing a dependence between the train and test samples because you're doing the feature selection based on information that's present both in the train and test data set. Okay, and then the second major category is you're using features in your model that you're not supposed to use. And the antibiotics for detecting sepsis, that's a simple example. But there are various others, but all of them we have grouped into this category of the feature somehow being a proxy for the outcome. So antibiotics being a proxy for sepsis. And how that manifests really depends on the particular task or the particular domain, but broadly speaking, this seems to come up a lot. And the third one, this is the hardest one. This is the one that's pretty close to distribution shift. So what's happening here is that you're making claims about a particular population, but either because of carelessness or because that population is not something you can sample from, you end up actually evaluating your model on a slightly different test set. And the performance you measure on the test set doesn't generalize to your target population. And that can in turn happen in a number of different ways. Okay, so here are some of the examples just to make this more concrete from the literature. So again, from the medical field, this particular systematic review found that a lot of studies simply didn't do a train test split. And, it's easy to say, what were these people thinking? I think we can at least try to understand maybe what happened in some of these cases, which is that I think a lot of folks are migrating from traditional statistical modeling where the goal is to explain your data. In traditional regression modeling, there is no train test split in statistics. Instead, you make assumptions about the data generating process. And as long as those assumptions hold true, you measure certain variables, the beta hats in your regression, or the feature weights in the language of machine learning, which are what is of interest. You're not trying to estimate predictive performance at all. You're just trying to characterize what's in your data. So I think a lot of folks are coming from that culture where you don't actually need to do a train test split, and then they're applying those same regression type methods to prediction problems where, of course, this is a very serious blunder. And this is an example of feature selection on the entire data set. So the train test split was performed after the set of features had been selected. Oh, and this, by the way, occurred in a very consequential area. This was a model that was used in social services for classifying certain children as being at high risk of abuse from their families. And this model was used to separate children from their families, which is, a devastating outcome for the family, maybe in some cases warranted if the child was at risk of abuse, but we really, really want to be sure that these models are correctly constructed and validated. Even after fixing the leakage issue here, the accuracy of this model isn't that high, and that's an issue I'll come to later, but on top of the fundamental limits to the predictability of these social outcomes, there was also a fixable leakage issue here. Here's another one along the same lines as the antibiotic. So these were models for predicting the onset of hypertension, and again, they used antihypertensive drugs as a feature. And this is a fun one. There are literally thousands of papers on diagnosing COVID from chest radiographs. When COVID started, this was, just everybody, I guess, dropped everything and started doing this. Several thousand papers. And one systematic review looked at 62 of those papers. And out of them, 16 used the same data set where the same control data set. So the positive samples, the COVID positive samples came from, some set of radiographs of COVID patients. So what is the control group you're going to use? That's hard. It's not the same data source that has provided the positive samples is not providing the negative sample. So what are you going to do? So you look for some other, pneumonia data set, I guess, in this case. And it turns out that all of those were pediatric patients. And so the model is simply learning to distinguish children from adults. And again, we might think this is so silly and easily avoided. But again, what are you going to do if you have positives from one data source and negatives from another data source? You can't really enumerate all of the ways in which those two might differ. So again, on the same theme, here is a system where different data sets come from different hospitals, and I don't fully understand this. My memory of the paper is a little bit hazy, but I think what happened here is that the way that these images are constructed in one particular hospital, they place some kind of object on the top right of the image. So that obviously leads to a feature which is very, very accessible to the model. And so it might easily pick up on that instead of whatever medical feature you're hoping for it to pick up on. So not to sound like a broken record, but to emphasize that point once again. So even though a lot of these may seem obvious, even once you've figured out that there is a problem, it's not easy to figure out how to fix it. And to explain this, let me go to an apocryphal example that is often used to explain what leakage is. And this comes from the early days of artificial intelligence, when the U.S. Army, and this is an apocryphal story. I don't know if it's true or false, but I'm just using it for illustrative purposes, and you can see the citation on the right. But apparently, there was a classifier which achieved extraordinary accuracy at distinguishing U.S. tanks from Soviet tanks. So people wanted to use this in warfare, right? Friend or foe identification. But it turned out that in the training and validation data, the Soviet tanks were photographed on a bright sunny day and the US tanks on a cloudy day. So it is simply learning to detect the background brightness of the image, which you can imagine would be very easy for a classifier to learn as opposed to the subtle differences between the tanks. Okay, right. So this is where the story usually ends. But the point I want to make is, okay, now you know there's a problem. What are you going to do about it? You might not have a source of photographs of, U.S. tanks on a sunny day, for instance. But even if you were, in charge of the army and you could get tanks onto a battlefield and photograph them on a bright sunny day, you still have not solved the problem, because there could be something else in the background. Maybe the type of foliage is different between typical US scenes and Soviet scenes, and maybe your model picks up on that. You can never be sure that you have addressed all of these possible sources of spurious relationship. Okay, so leakage is a well-known problem in engineering. If someone in the industry is building an ML model for ad targeting or whatever, they're all very aware of leakage, but actually they haven't been too worried about it. And let me explain why. So it turns out that in engineering, leakage is not as big a deal as it is in ML-based science. And here's the reason for this. In engineering, typically you build a model and then you would validate it, you would measure some performance, you're happy with it. You deploy that model in production. And engineers know that very often your deployment performance is going to be lower than your validation performance. They're already prepared for that. They're not trying to eliminate that possibility. So then when your model doesn't work as well as you thought it would, then you start to debug it and you figure out what the error is, and then you go back and tweak your model, right? So the mantra in industry is, to have these very quick cycles of fixing things, move fast and break things. And if your ad targeting model, doesn't perform that well, it's not a big deal. And you're not staking your reputation on the claim that the AUC of your ad targeting model is 0.78 or whatever. So all of these factors are different in scientific research. So we build models, we validate them, and then what do? There's no deployment, right? We're trying to contribute to the scientific literature. So we publish the paper, and then what? There's nothing. I mean, peer reviewers aren't going to check the model, right? That almost never happens. And almost never, no one ever tries to reproduce your study. And other people just take your findings at face value and then start building on that. And that, I think, is a serious problem. There's really, for all the dogma about science self-correcting, I think we actually fundamentally lack self-correcting mechanisms, at least when it comes to these ML performance claims, compared to engineering, where the self-correction tends to actually work pretty well. So errors can persist for a long time. They can persist for decades, and the stakes are also higher. And unlike in engineering, where you just want to know, do I want to deploy model A or model B, right? So absolute performance numbers are not that important. Even if you have leakage, your relative performance claim might actually be correct. So it matters much less in engineering. And again, all of those things are different in science. So to situate where exactly these problems occur, this is going to be a little bit of a busy slide. I apologize. So there's many types of machine learning research and applications, right? So there's, to start with, there's ML methods research, for instance. So this is your typical NeurIPS paper. And here, again, this is less susceptible to leakage because, leakage might often occur, but you're interested mainly in relative performance claims. We want to know, should I use a neural network for this, or should I use an SVM for this? Those are the kinds of questions people are interested in. And so even if there's distribution shift or leakage or whatever, those relative performance claims tend to be surprisingly robust to an extent that I didn't recognize until after I started doing this research. And if folks are interested in chatting about that, I'm happy to get into that in the Q&A. And then there might be ethics research, et cetera. I just put that there for completeness. But when we talk about applications of models where the goal is not to develop a new model, but to use existing techniques to detect COVID or whatever your application is. So we've talked about engineering and why it's less of a problem in engineering. And science is where it tends to be deeply problematic. And even within science, we can drill down further. So you can imagine various types of ML models in science. In a field like chemistry, you might use a model for material discovery. And I would consider this to be more of a search problem than anything else. So there is some large space of possible materials, and you're using this model to identify points in that space which might be particularly promising. And here, it turns out it's not that much of a problem. In my big table that I showed, there are no examples from chemistry. There are no examples from physics. And I genuinely think those fields are less susceptible to these issues, because once your model suggests a material, you can easily verify in the lab if the material has the claimed properties or not. So here, again, there is a straightforward self-correction mechanism. Where it does tend to be a problem is in these kinds of applications where you're trying to do a classification problem, as in the medical diagnosis domain, or, and I'm going to talk a bit more about Civil War prediction a little bit later on. But the idea here is that you're actually trying to predict some future event. And here is where we really, really lack self-correction mechanisms, because if you want to wait for the next 100 civil wars to occur, that's not a very useful way of trying to identify errors in your model. So these two types of research tend to be very affected. And even though this is a small part of the big picture of what machine learning research is, it turns out that this already covers, dozens of different fields and hundreds of papers in those fields, and probably many more that have not been analyzed. Okay. Actually, so let me go. So I said I'll talk about Civil War prediction. So let me go ahead and do that. So what we did was we looked at a series of papers that claimed that complex machine learning models, and I mean things like random forests, not like deep learning, compared to logistic regression. So the state of the art in Civil War prediction a decade ago was to use simple logistic regression models. And this was a new wave of papers starting in about 2016 or so that said we can use more complex models like random forests to achieve much higher accuracies at predicting the onset of civil war. The AUCs being claimed were in the range of 0.9 to 0.95. So as soon as we saw that, we kind of smelled something fishy, because if you can predict that a civil war is going to happen, people would just take steps to avoid that civil war, I think. And then there's scholarship in political science that says that's exactly the reason why wars are hard to predict, because if you can see them coming, you'll take steps to avoid them, because war is costly for all parties. And so we had some intuition along these lines. So we thought maybe there's more to this than meets the eye. So we started looking at these at the models in these papers, and it turned out that every one of them suffered from leakage. I apologize, this is a very busy slide, but the relevant part here is the 4 papers and their corresponding charts on top. So in each case, the left-hand column is the reported results in those papers for different models that were tested. And the right-hand column is what we actually found after correcting the leakage in all of those papers. And examples of leakage include, for instance, incorrect imputation. So in a lot of these cases, there's a lot of missing data, something like 70% of the cells today, even 90% of the cells are simply missing in your data. And what political scientists usually do is imputation methods. So they'll use machine learning to fill in those values based on the other values in your data set. And if you do that before you do your train test split, again, that's one of the types of leakage we've talked about. So once we corrected those errors, it turned out that random forests or other models, in fact, offered no advantage over decades-old logistic regression models. And this, this should match our intuition, because civil wars are hard to predict. There's not that much signal in the data. Whatever signal there is in the data can be extracted by these very simple logistic regression models. Now, one of the surprising things we found when we published this was the response from some of the authors. They claimed that these were simply methodological differences. They said, oh, no, in your machine learning community, you're supposed to do imputation a different way. But in political science, this is the accepted way of doing imputation or whatever. So in our field, this is how we do things. These are just methodological differences. Statistics is hard. Different people have different methods, and they come to different conclusions. So what I think is going on here is an interesting example of scientific differences that are related to cultural differences, and specifically explanatory versus predictive modeling. And I mean this in the sense of Breiman's Two Cultures paper, if folks are familiar with that, from back in 2001. This is a famous paper that talks about the different cultures in stats and machine learning. So in stats, or the explanatory modeling culture, the way things work is you assume a certain data generating process. You assume you know fundamentally how the world works, except for the values of some parameters, right? And then you're trying to estimate those parameters from the data. And because of that, there are different assumptions, there are different modeling choices, et cetera. And so, that's how statistics works. In predictive modeling, on the other hand, we don't make those kinds of assumptions about the true data generating process, right? And as I said earlier, that's why it's super important to do a train test split. And further, one difference in machine learning is that there is much less room for these genuine methodological differences that are matters of subjective judgment, because there is fundamentally, a ground truth. There is an external world, and you're trying to predict something in the external world. If there are two different models for Civil War prediction that make different choices and make very different predictions and have different AUC values, when you try to use those models to predict civil wars, one of them is going to work better than the other, right? So one of the ways of measuring your performance is correct, or at most one of them is correct, and the other one is wrong. So which one is it, right? So in the machine learning world, there are almost always correct answers and wrong answers. And so, at first we were shocked by what these political science people were claiming, but now we think it's probably because folks are coming in from this explanatory modeling culture that they probably don't recognize that the bar in machine learning is much higher, that a lot of these things that would have been genuine modeling choices are actually straightforward errors in machine learning. And so the other lesson from this is that in many cases, especially involving predicting the future, there's not that much predictability in the data. And so it doesn't matter if we keep pounding the data that we have with ever more complex models, we're not going to get better predictability. And things have, I think in some fields, I'm not going to say which ones, things have gone really wrong. We've heard from people after we published our paper saying in our field, there's a line of papers that claim an AUC of like 0.9 for some problem, but we know that all of those are erroneous. If we build the model correctly, the best accuracy we can achieve is 0.73. And so if we try to publish a paper showing how to build this model correctly, that paper gets rejected because it's below the state of the art, right? And so once erroneous papers get established as the state of the art, it actually becomes impossible to publish correct papers. So like really serious kinds of adverse selection effects are going on in many, many applied machine learning communities that are resulting in, a large prevalence of these flawed papers. And in fact, based on all of this, what I would say is that at least for the foreseeable future, until and unless there's a dramatic change in these practices, I think we really can't trust any absolute performance numbers from machine learning. If a paper says that model A performs better than model B, that's relatively trustable. Whereas if a paper says that the performance of a particular model is, 0.82 or whatever, I would take that with an enormous rock of salt. Because it's just a really hard problem to measure performance, and we're really not good at it. And I would not trust myself to do any one of these papers and be certain that there are no flaws in my measurement. I'm not exaggerating here. I feel like things are pretty bad right now. By the way, sorry, I don't have a slide on this, but there was a famous paper that looked at ImageNet, the image classification benchmark, and tried to generate ImageNet version 2, which is another data set that is sampled from the web in exactly the same way that ImageNet was sampled. And what those folks found, I think the first author is Ben Recht. I could be wrong. I apologize. Again, I don't have the citation in front of me. What they found was that despite following all of the instructions in the original ImageNet paper as closely as possible to try to come up with a new sample from the same distribution, the sample they ended up with was actually very different, because it's simply impossible to specify your sampling procedure in the finest level of detail, as a result of which models trained on the original ImageNet actually had an enormous performance drop when applied to ImageNet v2. And so even when someone goes to the greatest degree of care possible to come up with absolute performance numbers that can be trusted, which is what this paper was trying to do, it doesn't work, because you cannot specify your sampling procedure in really sufficient detail for someone else to be able to reproduce it exactly. However, what that ImageNet paper found was that the relative performance of models was almost completely unchanged. The correlation was more than 0.99 in terms of the hundreds of models trained on ImageNet v1 versus their performance on ImageNet v2. So I think there is a huge quantitative and qualitative difference between absolute performance claims and relative performance claims in machine learning. Okay, so let me take the last 5 minutes to talk about what can we do about this. So last summer, we ran a workshop where we wanted to kind of raise the alarm about the leakage crisis in machine learning. It was a virtual workshop and hundreds of people showed up. We were very pleasantly surprised by the turnout. And a bunch of us who spoke at the workshop and a few others, about 19 or 20 authors, then got together after the, by the way, the public workshop videos are available online if you want to look it up. But after that, we had a private workshop where we thought about what to do about this, and not just leakage, but the broader issue of reproducibility in machine learning. And we thought that many of these problems are due to carelessness or things that are avoidable, although there are some that are open research questions. And let's start with the low-hanging fruit. Let's at least avoid the avoidable problems. In a lot of cases, people are simply forgetting the number of details that you have to get right in order for a machine learning model to be reproducible. So let's list all those things. So we went ahead and listed that, and it doesn't even fit on one slide. So here's half of that list, and I know there's a lot of things here. So what we came up with is basically a set of guidelines paired with a checklist. So it's like part one, when you're doing your research, here are the things that you want to be mindful of at various stages of the modeling process. And then part two, once you've done your study, here are the things you want to make sure to communicate along with your paper so that someone reading it will have all of the information that they need in order to try to reproduce it. So I won't go through all of this, but let me maybe give a couple of examples here. Let me first of all mention that computational reproducibility, just sharing your code and data in a way that all of the details, including the libraries, whatever, are available so that someone can reproduce it and produce the same figures as in your paper. We're really far from achieving that. The vast majority of papers today don't seem to meet that bar. And we have some numbers on that in our study. The title of the paper is Reforms, and I should apologize for committing crimes against acronyms. Reforms is, it's the RE in reporting, and then the 4 here, and then the M from machine learning paste, and then the S from science. Bad acronym, but it was the only one we could come up with. Okay, so that's computational reproducibility. Even simple things like, why are you using machine learning for your study? I think every study should be required to report this in the paper, because a lot of the time, papers don't seem to have good reasons for doing that. For instance, again, going back to the medical field, someone might build a machine learning model to classify, I don't know, COVID or whatever, and then they'll use it to apply it across the data set and say, this is the prevalence of COVID in this data set. Okay, so what are you trying to accomplish with this? So you had to sample a training set in order to build your machine learning model. And whatever biases are in your training sample, that's going to be inherited by your machine learning model. And that's what you're applying throughout the data set. So how is this better than simply reporting the prevalence of COVID based on the ground truth in your training sample? Right? I don't think it is in most cases. So I think in a lot of cases, people are applying ML just because they can, and it just strictly makes things worse. I won't go through all of this. There's a whole bunch of others, and leakage is only one of the 8 categories in this broader set of reproducibility challenges. That's really the lesson here. And there were a whole bunch of authors involved in this. Okay, so I'm going to end with a little bit of a wacky idea. I'm curious if folks have seen automated data analysis tools, notably ChatGPT with Code Interpreter. Again, I said this was going to be wacky. I know this seems to be going in a different direction, but I'll explain what the connection is. And as someone who often tries to tamp down hype in machine learning, I hate to show you a hypey kind of a tweet here, but I'm showing it because in case you haven't seen this, you really should. I think there are problems with this tool, but it is also something quite remarkable. So if you haven't seen it, what this tool is, they're calling it advanced data analysis now, and they changed the name. What it does is you provide instructions in natural language, and it turns that into code, and then it performs that analysis on your data. And often it can perform analysis with almost no instruction. So in this example, it was just visualize trends, and it came up with all of these analyses that you see on the right. And this is a fairly straightforward example of what it can do. In fact, we have used this in some of our own reproducibility work. It often takes only half an hour to go through a paper and try to reproduce its data analysis and find errors. And that's a really good application of this tool because, like anything based on language models and generative AI, it can be error prone. We're aware that it can make errors, but it's a good tool for detecting errors, because once it has found what it thinks is an error, then you can then go and verify that error. So you don't have to rely on what the tool says is an error. So we've actually used this in our reproducibility work, and it's been very useful. So point number one is tools like this can be very useful and are being used. Point number two, these tools can also be really problematic. They can avoid important steps that are necessary for reproducibility. Point number three, can we actually modify these tools so that they incorporate checks for these known reproducibility failures throughout the data analysis pipeline? So that's what I mean by the title of the slide here. Can these tools actually be helpful for spotting reproducibility errors when a person is doing data analysis? And you might think, oh, I'm never going to use this tool. I'm an expert data analyst. Why do I need this? Totally fine. I'm not saying everybody should use this, but people out there are using it. I think there will be a day not long from now when a substantial fraction of machine learning-based research papers are going to be using automated tools like this in some form or another. And so even if you think these tools are not necessarily helpful, can we at least avoid them making things worse? And so I think it is imperative that people building these tools take these kinds of pitfalls into account and build those checks into the tools to at least minimize the likelihood that the analyses that are coming out of these tools suffer from the errors that I've discussed. Okay, that's all I had to say. I want to put up all my takeaways on the slide. I apologize. There's a lot of stuff here. I did say it was going to be a pretty broad talk. So I've told you that leakage is very pervasive. It has serious consequences, not just for the accuracy of the scientific literature, but also real-world harms. And I gave you examples from EPIC in hospitals and social services, et cetera. So we can be aware of the different types of leakage. Some of them are basic, we can avoid them, but others are open research problems like distribution shift. We need more research in those areas. Machine learning-based science is particularly susceptible as opposed to engineering, for instance. And so because of that, absolute performance numbers are not very reliable. And so when folks are shifting from explanatory modeling or stats to predictive modeling or ML, there are extra precautions that they need to take. And in many cases, I want to question if ML is even the right tool, because what we're trying to predict is not that predictable in the first place. Then I've showed you a little bit about the broader reproducibility crisis going beyond leakage. And it's possible that checklists, like the kind that we introduced in our reforms paper, could potentially be helpful. And then very speculatively, automated data analysis tools based on large language models could also be helpful here. Okay, that's all I have. Thank you very much.
Awesome. So thank you so much for the fantastic talk. I definitely learned a lot, and I'm sure that the audience are as well. So again, for the audience in the Zoom, please feel free to kind of continue typing in the questions in the Q&A. So I am just going to kick it off, redirecting the existing kind of questions that are already typed. Okay, so Arvind, I think one question that I see is from Thomas Gados. So he asked whether you could expand more on why the method research is more robust to kind of the leakage issues. So I guess you touch on that, yeah.
Yeah, absolutely, thank you. The main difference is that in methods research, so this is, again, your typical NeurIPS paper, people are trying to make relative performance claims. They're saying this new model is the state of the art. It doesn't matter if that state of the art accuracy, again, is like 0.93 or 0.92 or whatever. What others want to know is which model do I want to use? If someone has come up with a new technique, just to pick a random example from a few years ago, dropout regularization, let's say, right, for training your neural network. So, is that a good technique or not? Do I want to use dropout regularization in my model? So what that translates to is this model with dropout regularization, does it have a lower error than this model without dropout regularization? If there's some leakage, in the way you've set up your data sets, it's most likely, not guaranteed, but most likely going to affect both of those tests in a similar way. And therefore, the conclusion that you draw about, again, dropout regulars or whatever it is, that conclusion is mostly going to be unaffected. So that, I think, is the critical distinction. And related to that is that in ML methods research, we're not making a claim about some population of people or something else in the real world. We're just making claims about models. And again, that makes these claims a little bit more robust. So if we're saying that in this particular population of patients, the predictability of COVID is, whatever number, and therefore we should deploy this model in the real world, that claim is very susceptible to the details of that population and whether the data set you've set up accurately reflects that distribution of patients in the real world. Whereas if you're just making a claim about your model, it's not that susceptible to the gap between your data set and the real world. I think those are the two main differences. Thank you.
Yeah, that makes a lot of sense. So thank you for the answer. I think Yanis also has a question, given that Yanis is on the panel, so I'm just letting him kind of ask the question directly.
Yeah, thank you, Desiree. Arvind, great talk. Thank you so much. And I was extremely glad to see all of these leakage examples. And we have many war stories that thankfully did not make it to the papers because we detected them before publishing the papers. And also, I very much appreciate the message that, the more sophisticated nonlinear classifiers that are not so interpretable do not necessarily do much better than logistic regression. In fact, many of the instances where we have looked at, they actually do worse, particularly because, if you are careful with feature selection, then you can significantly boost logistic regression models. But the question I wanted to ask is the following: how do you detect, other than being smart, how do you detect, how do you work on these papers and sort of detect these instances? Is there some systematic way in which you can sort of test a new model and certify that there is no leakage? Or, I guess something that you can do is come up with a different data set and test it. That's one possibility, and then try to explain why it doesn't match. But are there other systematic ways in which, according to which, you can interrogate a model and identify these issues?
Thank you. Yes, I think there are two systematic ways. I don't know if either of them will get you to certification. Probably not. That remains an open challenge. But one thing that can be done is more centralization of data set collection and setting up of the problem. I think the ML community has done this well. Again, going back to ImageNet, one of the successes of ImageNet was that all of these tens of thousands of researchers really were using not just the same data set, the same train test split, et cetera. So it was the responsibility of one group to make sure that data set, had a valid train test split or whatever. On the other hand, when people are going about it in a decentralized way, everyone is doing it on their own. I think it's much more likely for errors to slip in and much less likely for errors to be detected, as opposed to when everyone is using the same data set and splits, et cetera. So that's number one. Number two is, again, this falls short of certification, but at the model level, I think if we have our data analysis pipeline, I think we have relatively systematic ways to take each of these known types of leakage or irreproducibility and check if they occur. If there's a new type of leakage that we haven't thought of, then it's a problem. But given that these are known types of leakage, I think we can do pretty well.
Okay, thank you.
Cool. So I would just continue kind of summarizing the Q&As. I think a few of them actually have asked you your thoughts about evaluation of large language models specifically, because it's currently kind of very popular. I know that you've kind of written a lot about kind of large language models. So I'm personally very curious about that as well.
So I actually had backup slides on that. Do you mind if I just take 1 minute to show some of those slides?
Yeah.
Okay. Okay, here we go. Let's see if I can. Okay, I think my slides are working. Yeah. So I think in large language models, there is also a potential for leakage. Notably, OpenAI has made claims, for instance, about GPT-4 passing the bar exam, US medical licensing exam. It's possible that some of those benchmarks are contaminated. We don't know for sure. We do know that one of the other benchmarks, which is a coding benchmark, was contaminated because we found that it gets almost perfect results on this benchmark before the training data cutoff date, which was in September 2021, and terrible results after the training data cutoff date. And we know this because this benchmark releases new questions every week. But for the medical and legal benchmarks, we don't have that nice way of separating by time. So we don't quite know that. But there is a deeper issue. By the way, when I say contamination, it's synonymous with leakage. And for some reason, in the LLM space, people use the term contamination. But the deeper issue is what is called construct validity, which is that when a person passes the bar exam or the medical exam, we know that they're capable of certain types of reasoning, which are going to generalize to the real world. But when a model passes these exams, what we suspect, based on what we know, is that it's much more based on memorization. Even if it hasn't seen that exact question, it's really relying on its knowledge more than its reasoning. And therefore, it's not going to generalize that well to the real world. So ways of evaluating these models that tell us about their real world capabilities are, I think, still largely an open research question. So that's my answer to that. Thank you.
Thank you. So I think there is another set of questions that, well, this one is very long. So let me try to summarize it. So this is kind of a question, I think Chad Minando. So I think he's kind of asking the question from a kind of, I guess, a health basically kind of health research perspective. And his point is that, well, in the health field, even though kind of most of the methods are kind of more kind of explanatory, the end goal is prediction. So given what you have shown in the talk, so the question is, how can we shift kind of the way to think about explanatory modeling so as to not carry them into the prediction or interventions in the future?
Yeah, that's great. Thank you. And I think lots of folks in fields that have traditionally done explanatory modeling have been talking about this. And what I'll say, this is a relatively, this answer addresses only one part of that question. I think it's a deep topic. I think if our goal is understanding, then explanatory modeling makes a lot of sense. I think in some cases, predictive modeling is overused in those cases. People use predictive modeling, they build ML models, and then they use feature importance, for instance, based on Breiman's techniques to try to understand what is going on in the data. I think that's actually very dubious. Those techniques, in my view, don't work well at all. So I think if the goal is to understand the data, we should stick with explanatory modeling. We should stick with stats. But if the goal is prediction, as you say, which is the case sometimes in medicine, then yeah, we should be using ML methods, but we should be very, very careful along the lines that I have described today.
Yeah, that makes a lot of sense. And then there is a question. This person is asking the question, do you think regulations, law, or industry kind of driven kind of code of conduct or kind of some other kind of, I guess, well, kind of standard setting as a potential way forward to kind of ensure better results in ML research and beyond?
Yeah, thank you. So there is a cluster of related issues here, right? So one is people are careless, and the other is there's a lot of pressure to publish, and a third might be, just not enough training, and a fourth might be in more commercial applications. Companies want to make claims about these tools that might not actually be supported by the data in order to sell their product, right? So I think it depends on what it is. If it's an issue of people being careless or pressured, et cetera, putting more regulations on them is not going to help because they're already in a situation where they're really, really constrained and they're not trying to cheat anyone. On the other hand, if it's a matter of commercial incentives being messed up and companies are not being transparent, and even if they're not cheating, maybe they know that it's the model is not that great, but they're not being fully transparent with their customers. In those kinds of cases, I think regulation is necessary. Just 2 days ago, I was on the Hill at one of the congressional forums that's going on this topic, and that kind of regulation is exactly one of the things that I recommended. Thank you.
Thank you. So I guess we are almost out of time. And I'm just going to pick kind of, I guess, well, if we have 1 minute left, we could kind of, I guess, like kind of pick one last question. Or so I guess, well, so the last question is, well, given what we know about the reproducibility kind of issues and especially leakage issues, how should we treat the papers that we already kind of discovered to have these leakage problems? Should we push the authors to kind of rerun the models, or kind of should we just kind of, I guess, like don't include them in the meta-analysis? So I think that's a question about kind of, you know, how do we kind of treat these papers retrospectively?
Yeah, thank you. That's a great question, super deep question. I'll say that one thing that has really helped shift my perspective is a line of writing that has argued that scientific truth doesn't reside in individual papers, but it rather resides in the kinds of models that we build that emerge out of collections of papers. And so I would see it less as an issue of, you know, what do we do about this individual paper? But rather I would think of it more in the sense of what processes do we need so that we can acknowledge that individual papers are always going to be flawed, but what processes can we have so that better scientific understanding emerges out of it collectively? So if you're talking about a field that has a robust culture of meta reviews, it's meta-analyses, et cetera, you're already in a good place. You know, I think a lot of scientific fields don't have that. And I was saying earlier that in medicine, people are at least doing these systematic reviews. So all of these processes that go beyond individual papers, I think as long as we have those processes, we're in a good place. I would really worry about situations where there's so much pressure that people are taking individual results for granted. And then there's pressure to, you know, keep building on the state of the art. That's really where I think the serious problems are.
Gotcha. Awesome. Thank you. So we are really out of time. We still have kind of questions from the audience, but I think maybe this is kind of a good time to kind of conclude. For the audience, if you kind of have questions, please feel free to reach out to Arvind. And again, thank you so much for this fantastic talk on this important topic. With that, please join me to kind of thank you again for Arvind to give this fantastic talk today.
Thank you. It was a pleasure. I appreciate the opportunity, appreciate the questions. Sorry we couldn't get to all of them. Happy to continue the conversation by email. Thank you very much, everyone.
Thank you.